Okay, so for part 3 of homework 7-5 here, we've got questions 8 and 9 to hopefully wrap up here. And question 8 is probably one of the trickier ones. It's definitely one of the algebra heavy ones, right? We know going back to these examples, they can be pretty challenging sometimes using the algebra. But anyway, the key to this question, they're asking after the release, how long does it take to reach the floor? Well, they give us the height. We know that it starts from rest, so we've got the initial velocity as well. So the key here obviously then hopefully jumps out as, hey, we need kinematics. And in order to do kinematics, I have to find the acceleration. Well, to find the acceleration, I have to do the acceleration of the system. And so obviously then I just need to make sure I am setting up my equations for both the forces of these two blocks and my equation for the net torque on that system, right? So anyway, we approach this much the same way we've done before, right? I know the net force on, I'll call this block 1, and then the net force on block 2, right? So I'm going to start by setting up my net force because that's usually a little bit easier. So my net force on block 1 would be the force of gravity of block 1 minus tension. And I'm going to go ahead and call this tension 1. Keep in mind we do have to have two different tensions in either half of the pulley here. Otherwise the pulley wouldn't be turning. So I'll call that T1. I also then obviously have the exact same type of equation, right? So the same type of setup for force 2, except for force 2 would be the tension 2 minus the force of gravity on block 2. Right, so I've got those two equations, but the problem, as we've seen many times before, is by using these two equations, I run into the trouble that I have more than two variables, right? I actually have three different variables. I have T1, T2, and I have the acceleration of the system, all of which I don't know. Right, so this would be m2 times a equals T2 minus m2g. So again, two variables there with the acceleration and tension 1, tension 2, and then on the first one here, m1 times a equals m1 times g minus T1. So again, I've got that set up as well. So because I get stuck when I use two equations, the goal then becomes I have to set up a third, right? I've got to set up a third equation. And the third equation is what's the torque on the system, right? So much like we've done before, we know that the net torque would equal the moment of inertia times the angular acceleration. So the net torque would equal the moment of inertia times the angular acceleration. The biggest trick on this one, the biggest change, is they also tell us that there is a frictional torque that does apply, so we'll have to consider that one as well. So let's break this down though, right? If I think about this again, the pulley is going to be rotating, in this case counterclockwise, and what that tells me is the torque from T1 has to be greater than the torque from T2. So I know that I'd have T1, the torque of T1 minus the torque of T2. But again, I also have the torque of friction, which is working against the motion, so I need to subtract that guy as well. And then over here with the moment of inertia, moment of inertia times alpha. They do tell me that this is a uniform disk, and because it's a uniform disk, and actually they may not say that, but they should have said that, that is a uniform disk, and because of that, I know my moment of inertia would be 1/2 mr squared. Right, so I've got that to plug in as well. So then at this point, it's a matter of just bringing everything together. Right, the torque caused by T1 would be T1 times the radius minus T2 times the radius, the torque of T2, minus the entire frictional torque, which we know that number, so we'll plug that in just a minute. And again, breaking this up on the right-hand side over here, be 1/2 mr squared, and then alpha is really the acceleration divided by r, so that can cancel out one of my radii on that side. So again, at this point, it just becomes a numbers game. It just becomes a matter of plugging everything in and being very careful with your algebra. So plugging everything in, being careful with the algebra. I'm going to go ahead and assume that we can do that. So again, just taking these equations, solving it for T2, solving it for T1, and substituting those in, and then again being careful with the algebra. I'm going to assume we can do that okay. And when we do that, I find the linear acceleration to be 1.61 meters per second squared. So I've got my linear acceleration now once I've done the algebra. Now if you do have trouble with that step, come find me and I'll help you figure out where it went wrong. Probably the most common mistakes would be either forgetting to distribute the negative to T2 or forgetting the radius on T1 and T2. So just check your work if you didn't get that answer. But anyway, now that I have the linear acceleration, I can just do good old kinematics to find my time, right? I know the initial velocity would be 0. I know the height. They gave me the height, my change in y, if you will, is 1.0 meters. And then I now know my linear acceleration is 1.61 meters per second squared. So since I have three pieces of information, finding the time is not much of an issue, right? Delta x equals v0t plus 1/2 at squared. Substituting the initial velocity for 0 simplifies that. My height of 1 equals 1/2 my acceleration of 1.61, and then times t squared. So solving for t, we get about 1.11. Started to read the acceleration again there for a second, but 1.11 seconds is how long it takes the system to reach the ground. So again, hopefully you're okay with the setup on this problem. It is definitely a very important problem to be comfortable setting up. Again, we've done these type of problems before. The only difference is when there is a massed pulley, when it is not massless, when there is a mass applied, you need to make sure you also set up the net torque for the pulley as well, and you keep the two tensions separate. But anyway, working through this problem, again, it is a big one, so if you have any trouble with this at all, come find me, let me know so I can help you out with it. But otherwise, hopefully you guys are starting to get more comfortable with this one. Okay, so then the final question of homework 7.5 here, question 9. And this one is a very nice combination of both torque and then our parallel axis theorem also comes into play. So they give us the sphere here of mass m and the radius shown. Notice that all of the measurements are just in variables, so our answer will be in variables as well. But a string is wrapped around the rod, pulls with tension of t. Find an expression for the sphere's angular acceleration. Right, so that's what we're looking for here. But anyway, the key is, what's the relationship between this tension and the angular acceleration? Well, if I think about this, right, I've got the rod, which if I think about the rod, it is basically a long, thin cylinder, right? And so the rod does have a certain radius, which they use a lowercase r. And then because the tension is being applied perpendicular to that, so as we're pulling the tension out, it's being applied perpendicular, that's going to generate a torque, right? It'd be a torque of the tension times that little radius. So that torque then is going to cause the sphere to rotate. And what's the relationship between the torque and the angular acceleration? Well, the relationship we know is the net torque equals the moment of inertia times the angular acceleration, right? So finding my net torque really isn't too bad. There's no significant friction, there's no significant air resistance or anything like that. So we've actually already kind of identified my net torque would just be the tension times the radius. That's the only force acting on this system. So if I want to find the angular acceleration, if I want to find my alpha, then I have to find out what's the moment of inertia for this sphere. And this is where you have to be careful, right? The moment of inertia for this sphere, because it's not being pivoted about the middle, will not just be 2/5 mr squared, right? It definitely will not just be 2/5 mr squared. Unfortunately, that is not what we can do. However, we can take advantage of the parallel axis theorem, right? And again, the parallel axis theorem says the moment of inertia about any point would be the same as the moment of inertia about the center of mass, which would be right in the middle of the sphere, plus mass times the distance squared between, where the distance here, the d, represents the distance between the center of mass and that position which we've pivoted it at. So say that 3 times fast, by the way, pivoted. Anyway, I can't say it once fast, but we'll move on. So if I want to find the moment of inertia for this particular sphere being rotated around that axis of rotation, I need to find this I based off of the center of mass and that distance away. Once I identify that, hopefully this question is pretty easy. Again, the center of mass moment of inertia here would be 2/5 mr squared plus mass times the distance from the center of rotation, which in this case they told me it was 1/2 of r. So it'd be 1/2 r, and I should, by the way, go over here and use a capital R, because capital R represents the radius of the sphere and the lowercase r represents the radius of the rod. They are different radii, right? Anyway, setting this up, at this point it's just a matter of calculating and getting a common denominator, right? So 2/5 mr squared plus this would be 1/4 mr squared. And when I do a little mathematics to clean this up, right, get a common denominator and go from there, I end up getting 13/20. This would be 8/20. This would be 5/20. So 13/20 mr squared. And that's the moment of inertia then of this particular sphere being rotated around that axis of rotation. So bringing this all together, my net torque, again, my net torque equals my moment of inertia times my angular acceleration. I now know my net torque is t times the lowercase r. My moment of inertia is 13/20 times m capital R squared, and then alpha. So solving for alpha, which is what they wanted me to find in terms of the rest of this, would be 20 t times r divided by 13. There's my 20/13, if you will, and then m capital R squared. And that, unfortunately, is not terribly clean, but that is as simple as it goes. You do want to make sure you're careful that you don't cancel again the radius out, because they are different radii for the rod and for the sphere. But anyway, good question to make sure you can work through kind of analytically here. Obviously incorporating the parallel axis theorem, which is a very, very big equation for us, and then also relating torque to angular acceleration, which is another key concept for us. But that finishes out 7.5. If you guys do have any questions over any of this material, I please do ask that you come in and get some help. I know this can be a tough chapter, but if you guys put in the effort, I am confident you can do very well with it also. So anyway, let me know if you have any questions. Otherwise, that concludes this video.